So in the last two sections of Appendix A, we start making use of these truth tables to prove statements, whether or not we're proving logical equivalence, whether or not we're trying to prove the validity of an argument. Those are the things we focus our attention on in these last two sections. So a lot of truth tables are going to come our way. And one of the things we're going to be looking to establish in some cases is whether or not we have a tautology or a contradiction. Now, a tautology is simply a statement that's always considered to be true. And the contradiction is a statement that is always false. Now, a lot of statements tend to fall into the category of, true in some cases, false in others. But essentially, when we look at, as we get more specialized statements, you have more of a chance to get one of these because that's what we're looking to establish, whether or not we have a tautology. Because logical equivalence, if I want to give it an alternate definition of it, basically if I have two statements that are supposed to be logically equivalent, then if I take those two statements and write them as a biconditional statement, they should be a tautology. So basically the biconditional of those two statements should be true. And we have numbers of laws of logic for the, for these, various propositions and things like that, and these logical equivalents. I put a bracket around the last two because, those are really the two that the most students have the most trouble wrapping their heads around. The other ones kind of make sense if you think about it. Like P being true and P being true is the same thing as saying P is true. Well, yeah, it makes sense. P being true or P being true or both means that P is true. Again, that just kind of makes some natural sense. 9 and 10 often throw some students off because, not only if you take a disjunction, an or statement, and combine them and negate that statement, you actually end up with a conjunction of the two negations and vice versa. And that sometimes throws students for a loop because they're like saying, well, that shouldn't happen that way. That doesn't make any sense. But if you think about it, it does, and we could actually prove it to be true. So let's show a simple proof first. For number 5, the commutative law for conjunction. I mean, this kind of makes sense. Saying, well, if P is true and Q is true, that's the same thing as me saying Q is true and then P is true. Do I really need a formal proof for that? Not really. But this just wants to show you a statement is true. Well, how do you recognize it in a truth table as a tautology? So I have these two statements. I don't know what they represent, but I'm just going to put every possible combination of the two. Either they're both true, one is true and one is false, which the middle two are taking into consideration, or they're both false. So now I'm going to look at the statement P and Q. And again, P and Q is only going to be true if P and Q are both true. It's false otherwise. And likewise, if I say Q and P, well, it's only going to be true if Q and P are both true and false otherwise. As I can see, the columns underneath these last two are exactly the same. And that's what makes them logically equivalent. If I get the exact same thing for the truth table values, all the way across the board, then they're logically equivalent. If one of these was different, then they would not be logically equivalent because there would be an instance where that's just not going to work. This one here is a little bit more, pressing because some students don't know whether or not, they have trouble wrapping their minds around this. So I want you to pause for a moment. I want you to construct a truth table for this. I'm not going to have you enter it into play pause it because that would be quite an undertaking. But I want you just to write it out there, and we'll come back in a second or two, and we'll compare our truth tables. Okay, so now we have this, and it's these truth tables that eventually you're going to need to be showing me to show that you know how to come up with the right conclusions and things like that. So, so to prove this, again, I'm going to start with, since P and Q are the two arguments involved with this, I'm just going to start with P and Q and every combination of them being true and false with respect to each other. And now I'm going to look at P or Q, which we know P or Q is true only in the instance, basically it's only false when both of them are false. It's true otherwise. So I end up with this truth table. And of course, when I negate it, I end up with this. So, I have the left-hand side now. Now I want to look at the right-hand side, which means I need to figure out what not P and not Q are. Now, I look at these two columns, and all I'm going to do is negate them. If I negate P, everything that's true in that column is going to be false in not P, and vice versa. For Q, same thing. Anything that's true in Q is going to be false in not Q, and vice versa. So I end up with these. And now I'm going to do the and statement between them. Now an and statement means that it's only going to be true as long as both are true. It's false otherwise. So what I end up with here is that I end up with the first three instances of them being false, and the third one and the last one being true. Now when I look at the column that represents the left-hand side and the column that represents the right-hand side, they're exactly the same. And as a result of that, I've proven De Morgan's law here that this is a true statement. So, for this one here, I want you to take a moment. The laws of tautology and contradiction, they have all these rules, but it's one of those things that I found that you don't need to have these rules stated outright. Some of it, if you just get enough practice with this, it just seems to make sense. Okay, I want you to go through and construct the necessary truth tables to tell me whether or not this is a tautology, a contradiction, or if it's neither. And then, we'll compare our results. Okay, so when I start the truth table for this in order to come up with this answer to this question, I'm going to first, keep in mind that I do have an order of precedence for logical connectives, like my order of operation for, dealing with algebraic expressions. Anything in parentheses would be done first. Negation would be done second. And would be done third. Ors would be done fourth. Conditionals fifth. And biconditionals sixth. So basically, since I have all this stuff occurring on the left of the arrow and one thing on the right, these are kind of telling me that all of this is kind of grouped together. And I only have P and Q involved with this, so I'm going to start with all the possible combinations of truth values for P and Q. And remember, a truth value is just true or false. Okay, so I'm going to look at if P then Q, which is part of that statement. And that's what's in the parentheses. And basically, again, it's true. It's only false when P is true and Q is false. It's true any other time. So that's why I get this truth table. And now I'm going to look at the P column and this column to come up with P and if P then Q. And basically, for that fourth column to be true, both of the columns I have circled have to have to be true for a truth value there. So, as I see there, I have that being the case for the first line. The second, third, and fourth, I have one true, one false, so it's going to be a false statement. Now I want to see, what happens with Q. The thing is now, this right-hand side is my hypothesis. And this is my conclusion. Remember that an if-then statement, which is what this thing is here, it's basically only false if the hypothesis is true and the conclusion is false. What I see here is I have the hypothesis being true in only one instance. The Q value is also true at that point in time, so it's true for that. Everywhere else, the hypothesis is false, and as we said for a conditional statement, it's automatically the case that if the hypothesis part is false, then the conditional is true. So, as a result, my truth table will look like this. And as I can see, I have nothing but a column of true values down here. So as a result of that, this thing is considered to be a tautology. Arguments. Now, an argument, I mean, we've been doing some arguments already, just not like some of the involved statements that we would tend to do. But, you know, an argument or proof consists of a set of prepositions called premises and a proposition Q called the conclusion. An argument is valid if and only if the conclusion is true whenever the premises are all true. Otherwise, it's considered to be false or an invalid argument. I'm not going to get into this. I mean, it's talking about being a tautology, but it's actually better to look at it from the perspective I'm going to be showing you. So, the first example I'm going to walk through first. I'm going to let you do the other two first before we get into it. So, determine if the following argument is valid. So, we're basically being told that if P is true, then Q is true, and we're also told that it happens to be the case that Q is not true. Therefore, P is not true. Is this a valid argument? So we're going to test that out and do a proof to see whether or not, you know, this is a valid argument. So, since P and Q are the only premises I'm working with here, I'm going to make a list of P and Q truth values and all the possible combinations between them. I'm now going to make truth tables for each of the premises now. If P, then Q. Again, only going to be false if P is true and Q is false. It's going to be true otherwise. So that's where I get this truth table from. Not Q is going to be me taking everything from the Q column and negating it. So everything that was true was false and vice versa. And I did the same thing with not P because that's my conclusion. So I have the three statements here, the two premises and one conclusion, all in my truth table now. Now what I'm going to do is look to compare them. So I'm only going to look at the cases where both premises are true. So that means that the third and fourth column, I'm only looking for cases where I have the truth value of true in both of those. That's true only here. They're both true here. Now, if both are true, then for this to be a valid argument, then the conclusion has to also be true. And that happens to be the case here. Therefore, this is a valid argument. So, now I want you to take this and try your luck at this one. Determine if the following argument is valid. So, I want you to state whether or not this is a valid argument. Make your truth table and, you know, give me an answer. Okay, so again, now this one here, I have three basic statements that are being tested together, P, Q, and R. So I'm gonna first start off with all the possible combinations of truth values for those three variables. And now I'm going to try out the two premises and the one conclusion and come up with, you know, truth tables for those. So if P, then Q, again, only going to be false if P is true and Q is false. So I do have two instances of that. It's true anywhere else. So that's how I get that truth table. Q and R, that's only going to be true if both Q and R are true. It's going to be false otherwise. So the truth table for that looks like this. And then P or R, only going to be false if both of them are false. It's going to be true otherwise. So I have this is the truth table for that. So I have the two premises and the one conclusion mapped out on my truth table. Now I'm just going to focus on the instances where both where I have the fourth and fifth column showing true statements in both of them. So I'm looking at these two. When I look at both of these statements, the conclusion is also true, the P or R. So based off of that being the case, the argument is indeed valid. For the last one, This is more wording. One of the things that you're going to be asked to be able to do, and I'm going to start you off on this to help, is that you're going to need to quantify these using symbols. So you have, if Tony is wealthy, he is either intelligent or a good businessman. Tony is intelligent and he is not a good businessman. Therefore, Tony is not wealthy. Is this a valid argument? So we're going to work under the premise of this. We're going to let W be the case that Tony is wealthy. We're going to let I be the case that Tony is intelligent, and we're going to let G be the case that he's a good businessman. So if I translate these into statements, the first one's going to be if W, then I or G. The second premise is going to be translated I and not G. And the conclusion is going to be stated as not W. So, with these being translated for you, I want you to tell me whether or not this is a valid argument. So make your truth table and make your determination. Okay, so you've determined whether or not this was a valid argument. Let's see if we come up with some agreement here. Therefore, I'm going to start with the three basic premises, the three statements, and come up with every possible outcome, truth-value combination for those. So, there they are. It's every possible combination of truthness and falseness between those three variables. I'm going to start with doing I or G, because that's going to be that's one of the things I have to look at. So, again, if I look at I or G, that means it's going to be true as long as at least one of them is true. It's only going to be false when both of them are false. So that's how I get the truth table here. Now I'm going to look at the case at not G, because that's another premise that I haven't really tested yet, or part of a premise. So basically I'm just looking at the G column and reversing all of the truth values. So anything that was true for G is false under not G, and vice versa. So now I can get into creating these premises, the truth table for the premises. So the first one, if W, then I or G. So I'm looking at this column here, and I'm looking at this column here. I'm looking at the first and fourth columns. Now again, for this to be true, the only time it's going to be false is if the W column has a true and this column has a false. That only happens once. Okay? Otherwise, I either have them both being true, or W is false and it's automatically going to make this a true statement. So now I'm going to look at I and not G. So I'm going to look at the second column and the fifth column. And for that to be a true statement, those two columns have to both have a true statement in it. It's going to be false otherwise. So I end up getting this for truth values. And lastly, I'm going to make a column for not W, because that's my conclusion. So I'm looking at the first column, and I'm just going to reverse all the truth values for that. So those last three columns are I'm now going to focus my attention on. I'm looking for instances where the green and purple columns have trues in them. So I have two instances of that happening, where both of them are true. Although I have down here that the two true statements lead to a true conclusion, I do have an instance right here where I have two true statements and a false. For me to state it's a valid argument, everywhere I have but all the premises being true, I have to have the conclusion being true. Even if there's just one instance of all the premises being true and the conclusion being false, the argument is not valid. So it's not valid to conclude that Tony is not wealthy based off of the information that we have here. So this argument is not valid, it's invalid, it's a fallacy, whichever you want to call it. And that's the end of this. If you have any further questions, please make sure to bring them up in class. Make sure you practice. Now you have the ability to hopefully work on all the homework problems at this point. And again, if you have questions with any of those, you're going to ask about them in class. That's all I have for now. Until next time, have a good day.